No, it's all good. Thanks. Yeah, let me share my slides. All right. All right, so it's great to present to you guys. I hope it's not too late, but I can see that it's really dark outside. Yeah, let me share my slides. Can you hear me well?
Yeah, we can hear you.
Okay. I just heard like echo of. All right. So today I want to talk about my recent work on machine translation called "Attention is All You Need," and this is work done while I worked at Google with a team of great researchers there. Just to kind of expand a little bit on my background, I worked at Google Research for about 3 years, worked on various natural language problems, led the question answering team. So if you ask questions at Google in English, some of them are answered by deep learning models we built. And I worked on TensorFlow a lot, building an estimator interface and a lot of other internal parts. Now I'm a CTO at Near.AI, where we're teaching machines to program. So we're trying to build a system that you can just talk with and it will program for you. So yay. We're currently at research phase and we're looking for collaborators and hiring, of course. So if you're interested, hit me up. All right, so deep learning in general had revolutionized NLP. I would say about 3 years ago, we would use pretty much either regexes or bags of words and n-grams for most of our work. But kind of throughout the last 3 years, recurrent neural networks pretty much changed how we do natural language processing and achieve state-of-the-art across many tasks, from kind of parsing, tagging, to machine translation, question answering, etc. And translation is really great recent example where the kind of big neural network models beat up the 20 years of work of researchers kind of across the field and just replace the whole system. Both in Google, Facebook, and a few other places kind of deployed it in production. And when you go to Google Translate now, it's actually a huge deep learning model. So what is kind of a driver for translation, specifically sequence-to-sequence models being the main kind of improvement? And the idea here is that you have a sequence model that reads your input, for example, can be in Russian, and then outputs in English the kind of transformed, translated representation. And you train it end-to-end where you feed into the decoder part, the part of the decoder, the English translation you want, you kind of backpropagate the error, and neural network tries to learn representations that's useful to do this kind of task. Now, there's few issues with this, and kind of issues are general for recurrent neural networks. And first of all, because this is a sequential model, right? You have to read next word only after previous word. You have a problem with parallelization. You cannot read all the words at the same time. So if you have sequence of length n, it takes n steps of processing. And like at the scale at which we have training data for translation, that becomes a big issue. The second one, which is actually a learning issue, is that backpropagation through the sequence has a lot of kind of effects, and these effects being like battled through gating, through all kinds of mechanisms in recurrent neural networks themselves. But the idea is, because you have this long decoder, your error either can diminish with every step as you kind of get to the source of the signal, or it can expand and you kind of have this exploding gradients. And in general, like, you need to kind of step through every previous, maybe correct decoding to get to the encoder part and actually find and propagate the error of the of like why you produce, for example, a wrong word. So this all kind of hinders your performance, as well as takes really long time to train. And kind of another part is that you're pretty much transmitting a lot of information through the bottleneck, right? You have encoder and decoder kind of combined through the bottleneck of hidden state, and you want to transmit kind of global information about the sentence, right? What is the meaning of the sentence, as well as a lot of like local things, right? Because let's say we have word Google there or word Apple, and for the meaning of sentence, both of them are companies, so you don't really need this information in the kind of global state of things. But when you're translating, if you say instead of Google Apple, that would be a huge mistake. So you kind of both transmitting this two pieces of like very different information. So there's been a kind of variety of work done to address these issues. A lot of it is trying to use convolutional models, which have performed really well on images for text. And the idea being convolution kind of gives you a window function that processes like few words, let's say, together and produces some encoding. And you can hierarchically stack them to pretty much propagate information from any end for encoding. And then you can perform the same operation on decoding. And that's where it becomes complicated. But notable work is Neural GPU, ByteNet, and recently from Facebook, convolutional sequence to sequence. But all this is kind of limited by kind of size of the convolution, meaning you can only propagate, let's say you have size of convolution 5, only 5 words of information are combined in the context. So you need to build enough hierarchy of these convolutions to combine information from the first word with the last word. And in languages like German, for example, where the word nicht, meaning not, for the verb goes at the end, you actually need to like combine this information really well. So this requires to have really deep neural networks, which is great, but still kind of adds up on the kind of both performance of the model and how well it trains. The other work, kind of dimension of the work being attention. And attention is a mechanism that allows to, while decoding, while kind of writing out, let's say, translation of the sentence, to look back at the actual sentence we are translating and in the context bring some information. And see on a graph, kind of the idea is for the time t, you take in a context vector from the previous time step, and you kind of looking at all the outputs of the encoder, figuring out which ones are the closest in some projection, and bringing that information to the next time of the decoder. So if you think the example where you're translating a sentence like company Google acquired something, you can think of the meaning of the sentence, something acquired something, that's kind of passed as a regular hidden state, but then the specific information that this is Google acquired, let's say, I don't know, YouTube, this specific piece of information don't need to be propagated anymore through the hidden state. You can actually look up which specific company did it acquire, which specific company was it, and bring that like vector of information back here, translated, which for common now for names you don't need to, and pretty much output. There's one major benefit is that backpropagation now is pretty much direct, right? So when you're making an error, you said instead of Google, you're saying Apple, this error directly goes into the attention and goes into encoder. So your vectors can kind of adjust really quickly. And that's pretty much the kind of state-of-the-art model been there before this work, is applying this attention mechanism to very deep recurrent neural network. I think it was 8 layers of recurrent neural networks. encoder-decoder with attention. Now, the idea behind this work is self-attention. And the kind of idea behind self-attention is that if you're already kind of using attention mechanism to look up information from different places, why not, for representing the sentence itself, for the encoding, use the same mechanism? So let's say we have this sentence, let's represent the sentence. We embed it, as usual, words into some high-dimensional vectors. And then for each vector, we're using the same attention mechanism to compare it with all other words, right? So we compare R2 in this case with representation of word 1, word 3, and word 4. We're receiving kind of the vector similarity of this projection that we got, and then we combining these vectors now back with the representation of its own word together. So now we know kind of in a general sense how this word relates to other words in the sentence. Together with information about this word, we use just a fully connected layer, and now we have a new representation that we can use for other processing. And here you can it can learn to combine information that it needs, right? It can resolve, for example, if there's a nicht for German at the end, it can look up into that and brings that information that this is actually a negated verb. It can, if it's multiple word nouns, let's say, it can combine that information together, etc., etc. Resolve anaphoras. So this work, like self-attention in general, is not new. Throughout 2016, there's been a lot of work on kind of using this mechanism as addition to a lot of things. Except the last decomposable attention model, everywhere else they use this mechanism combined with recurrent neural networks. But if you think of it, what kind of comparing this mechanism with recurrence and convolutions, and we want to compare it on specific axes, right? We want fast processing. We want as much parallelism as possible, and we want backpropagation to be have the least possible lengths, right? So recurrent neural networks, right? The complexity is the length of the sequence multiplied by square of the dimension of hidden state, because inside you have a matrix multiplication, which is d squared. So, and you have sequential operations, right? So you have n tokens in the sequence, and this is also the length you need to propagate back. Convolution, the complexity of it is the kernel size multiplied by, again, square of the dimensions as you processing it, and by length. But you can do that in parallel, and the length is how many hierarchy you have to propagate. What self-attention brings is actually pushing this. The complexity now is on the length of the sequence. So you have n squared because you want to attend pretty much every word to every word, but you only have one multiplication there, so multiplied by d. And if you think for machine translation and a lot of natural language tasks, the n is usually low, right? You usually have maybe 100 words in your sequence, but the dimensionality of vectors is usually 250, 512, 1000. So just moving the squared from d to n is already giving you less operations to perform. And then because all operations can be done in parallel, you can multiply any of these things in parallel. There's no, just pretty much everything can be done in parallel. And the same is when you're backpropagating, the attention can use to find where information is to be propagated. Now, n squared by d can be a little bit overwhelming. So there's also a version where you're using a local attention or restricted attention. That's where component of R coming in, where you're only attending to a window around you. So you still need some hierarchy to propagate information, but gives you a little bit better performance if your n is large. But this idea is with self-attention, we can replace recurrent or convolutional networks. They will run faster, and their propagation is of information faster. So how does it look in practice? So here's kind of schematic of how this model can work, right? So for decoding step, this animation started a little bit late. All right. Yeah, so for encoding step, right, you have the sentence, you kind of taking each word, and each word combines information from all the words, right? And you do that for some number of kind of layers, because we're doing deep learning, so yay. And then for decoding, you can do kind of the same operation. At inference time, you still need to kind of decode one word at a time. But at training time, you can actually also combine information from all previous words at the same time in parallel. So that's kind of an idea behind it, using self-attention to combine information from local words, and then use the same mechanism to decode one word at a time. So how does this look? You have an encoder-decoder model, same idea, but instead of having a recurrent unit, you have this transformer unit. Transformer unit contains pretty much attention mechanism and feed-forward network with some pretty much layer norms to help with propagation and training. And you have few additional kind of components to make this work. So on the encoder side, the one interesting thing here, when you embedding your inputs, you adding the positional encoding, which I'll talk in a second. Now this combined vectors, you're using pretty much multi-head attention to kind of combine the information, layer norm, feed forward, and that's your kind of sentence representation, then variable size sentence representation, right? And on decoder side, you first kind of attend to all the decoded words so far. So this is masked attention. So you mask kind of looking at words only that came before the specific word. And then using that information, you now attend to all the words from encoder, all the representations from encoder, and that kind of goes as a decoding for this word. Now, for the model kind of results, 6 layers of which were used. I'll show you in a sec the results and kind of ablation study, but that's kind of general idea. Now, just to talk about it, multi-head attention, kind of general idea is with one attention mechanism, you can pick up one piece of information. What happens when this word wants to relate to multiple words, right? In kind of regular attention, you would bring pieces of information with kind of lower weight, but why not just have multiple kind of attentions for each word at each position? And kind of just simply you expand the attention mechanism, let's say for this model we used 8 times, so you can use up to 8 kind of different pieces of information brought together. And there's also one additional kind of trick was that in attention usually is just kind of multiplication between what you're trying to kind of query with to what you're looking up into, and then you softmax and you're getting the result. We added a scaling because with kind of this large of sequences, the kind of gradient propagates better when it's scaled. So that's the scale dot product. So this all combined gives you kind of a mechanism where for a bunch of words, let's say input encoding, you at the same time for each word can bring information from a bunch of places, put it all together, and process the next step. Now, what is positional encoding? So if you think of it, we don't have a recurrent neural network inside. And recurrent neural network, the kind of benefit that it gave is that it has a kind of sequential understanding while it's reading the input. But here, we're kind of using each word independently, So if we actually shuffle the words in the input that we give into the model, it doesn't matter. So we need actually to give information to the model about how words are related, like positioned to each other in a sentence. And this is the idea that you want to give this kind of positional encoding. So there's few ways to do it. One alternative way is to just, for each position, you assign some vectors that you learned, and you let model learn what that vector should be. The problem there is that you cannot then use dynamic size, right? You need to have fixed size of this of the input and output so that vectors are learned, and that's not great because also the last vectors will not learn very well because the size of the sentences varies. So the alternative is to actually use a kind of decomposition into sinus cosinus of the positions. So kind of generally each positional encoding, right, is some vector of pretty much the same size as your hidden state in the model. So you can, for each position in that vector, assign some kind of decomposition with a different kind of moving on the circle with a different speed, pretty much. That's what it is, right? So you're saying that, you know, position 1 is kind of all of the vectors is 0, and then as you move into positions, you have kind of multiple pointers that move with different speed. So which allows inside the attention itself for model to understand the distance between words, right? So when it processes 2 vectors and kind of compute the dot product with them to compute attention, it like multiplicatively can pretty much compute some metric of a distance inside it. So kind of what this all resulted in. So this is evaluated on translation of English to German and English to French. English to French is like very well studied, and it's also seems like easier translation. English to German is also well studied in literature. There's been a lot of work, as I mentioned. GNMT is the one that kind of Google first launched in Google Translate. Conseek2Seek is Facebook model, ByteNet from DeepMind. So there's a lot of work being done. And kind of idea here is that additional to the just score, we also want to look at how much it took to train. So the evaluation metric is blue score. Kind of general intuition for it is matching the n-grams of the sentences translated to ones that are kind of, we know, correct translation. And generally, it's not the perfect metric, but it's shown to be correlated with real kind of real people looking at the translations and judging them. So the kind of transformers pretty much for the bigger model outperform on both of the English to German, English to French. But the main idea here is that training cost is pretty much 1 to 2 100 times faster to train. And it's not just 100 times faster, it's also much more parallelizable because with GNMT and pretty much all the sequential models, you need to read in each sequence in kind of step by step, which doesn't allow you to parallelize it. So they had like hundreds of GPUs to train that for a long time, for I guess 2 weeks. And the transformer can be trained on one machine with 6 GPUs in 1 day. That's kind of the speed up you get from this, which allows, of course, to faster experiment with this. And you can see that some ensembles can beat the model a little bit, but of course with ensemble you get more training cost because you're now training like 10 models instead of 1. To show you how kind of varying different parameters changes results. So the base model is 6 layers of transformers, 512 the kind of dimensionality, and 8 heads. H is number of heads in the attention. Training steps 100,000, and kind of you can see that like changing the number of layers kind of somewhat changes the results, but also dramatically changes number of parameters, so you can kind of balance it out. And then big model is pretty much expanded hidden states and expanded fully connected layer, more heads, longer training. That's what gets the best results. So still bigger model is better. But for experimentation, you can go to, for example, 2 layers of transformers, and you can still compare these results while getting much faster training. So to give you some intuition behind what's actually happening, right? So there's one more reason why attention is such a great machinery, is because we can look at it. So when attention happens, right, you can look at the vector of attention that that dot product produced, and look at, for example, here you have a word making, and you have 8, I guess 7 was one really hard to see, heads shown. So this is only like one word attention displayed, where each head is shown where kind of mostly attended to. And you can see that for making, it both attends to making itself and to more difficult, right? To the words that kind of combines this into one phrase. So it combines the information about more difficult into the representation of on this position for a future processing. Another one is pretty much an upper resolution, right? You have the law application, and it's pretty much referring to that, to the law. So it combines this information together in its, so for future processing, right, it can understand what is it's talking about. And like this has been actually a huge problem in natural language processing for years, and been like, there's a lot of papers around it, how to do specifically this modeling, but the attention only need model actually can learn this kind of relationship inherently. Now just showing one specific head, as you see, kind of combines information from core words, right? So on the bottom, you see previous layer, law, application, missing, opinion, and this information kind of propagates into all of the other words to kind of give the background on what's it's talking about. Just kind of give you more of this relationship where kind of in the lower layers it's just combining the local, very local information instead of kind of getting global. Now, to kind of show this is not just for translation, we've done some experiments on constituency parsing. So if you're familiar with natural language processing kind of toolkit, there's tagging, and then NER, name entity recognition, and then there's different types of parsing, where you want to build some kind of tree structure out of the sentence. And if you think of it with sequential models and results attention, you don't really need this mechanism as much because machine learning learns this mechanics. But it's really good setup to evaluate if it learns these things itself. And we can show that, yes, this model performs very well, given it's not like fine-tuned in any way to kind of perform the best. It actually beats most of the models except some new generative ways of doing this. So definitely beats all the semi-supervised models that been there before. So idea here, it actually learns the dependency between kind of words, and you can crystallize it into some classification label saying, well, this is a verb, it relates to this noun, to this, this is a subject, this is an object, prepositions, etc., etc. So it builds this kind of tree from the information that transformers learned. All right, so questions, that's pretty much it. to few links, tensor to tensor on a TensorFlow repository contains all the code for these models and more, so you can just kind of check it out and start training your models for whatever languages you want or for whatever tasks you want to. There's a blog post with some more information, and here's my email.
Okay, guys, let's first thank the speaker. And do you have any questions? Okay, if you have any questions, could you please just come here so that Ilya can also see you?
Okay. So concerning positional encodings, I didn't quite get it. Why did you decide to use this? This synesis and cosinesis. Was it even your idea? I mean, how did you
come up with this?
Yes.
All right. So, well, it definitely wasn't my idea. So we tried a bunch of stuff actually. So we started with, as I said, learned encodings. So we gave a vector and we trained it, but it has kind of problem with not scaling with the size of the sequences. So we tried different type of kind of encodings that changes with the position, right? But allows to attention mechanism to pretty much compute this distance. And pretty much this worked relatively well. But the intuition behind it, as I said, is you can think of let's say for position X, right? It's you have, let's say, 500 values, and each of these 500 values is kind of a position on a circle, right?
Okay.
So sinus and cosinus can represent it like position on a circle, where it depends on X, right? With you kind of rotating on the circle with different speed at different of these 512 positions. So if you kind of think of, some decomposition where as you kind of move on one axis, right, you rotate around the circle, right? Then there is a.
And what do I get in the output? I mean, I have my embedded words, and I want to get to have this like positional encoding. What do I have for every word? I mean,
so you sum this kind of rotation in a circle with the word embedding. What happens there is this kind of positional circle gives a little bit nudge to the word.
So it moves a bit like my word embed. Okay.
So it moves them a bit in some very small kind of radius inside, and then when doing the dot product between two word vectors with this positional encoding in them, now it can actually understand how far these words are in kind of your input sentence, right? So the multiplication of this gives you kind of the distance inside the inside the operation.
Okay, well,
so this allows, for example, you have word at the end and word in the beginning, right? You will, and let's say you have the same word next to the first word and at the end, right? So one, like if you didn't have position encoding, right, the dot product between them would be the same. Like attention would be like equally split between them. But with this positional encoding, it will compute the distances much closer to the word next to it. So the attention will be put mostly on this word, even though it's kind of the same vector from the input.
Okay. And the second question is, have you tried this model with like full attention over all words, in the sentence. I mean, you've mentioned in the beginning about that you used a model that will give you a complexity of R times K times N, you know, so you use a window. Have you tried it with the full sentence? And does it make sense? Especially the more interesting here is what the R is like most optimal for this way of.
So actually, all these results are with a full attention.
Ah, okay.
Because for the translation, for these data sets, the length of the sequence is about like 120 maximum, and mostly it's like around 50, 60 words. So the attention is actually fine. But for example, I'm using this model on sequences of like 5,000 links. So 5,000 squared is a lot. So I'm using this restricted one. So it's mostly for a background. But yeah, for this specific work, we use the full attention. And yes, it makes a lot of sense because you get like more information about kind of sentence as you're doing it.
All right. Thank you.
Sure.
Any more questions? Okay, please come here.
Thank you for your talk. Is there any experience on trying these things on images? Because as far as I understand, if you have a restricted attention, these things may look like convolutions with custom filters at each location, right?
Yes, so it's a good question. And actually, there is a paper for ICLR with images that Ashish, the first author on this, sent out. I'm not super familiar, mostly because I believe images are kind of easy, so we should focus on text and reasoning and understanding. But it's definitely true that like this is very especially like restricted attention is very similar to like convolutional filters. Yeah, with masks, it allows you to do a lot of the same things. They're trying also to do all kinds of additional kind of customization, how the attention can work, and how like you can learn pretty much a filter. Like there's this hyper networks where you're learning filter with another network, so they're trying that too. So there's a lot of commonalities with convolutions, but it also allows you to do this in a more parallel way, as well as kind of combining more signals.
Okay, and maybe one more question. Are there any ideas how to make these things more like non-autoregressive, so that even in inference we can... I mean, yesterday we had a talk that introduced some very complex things that were getting closer in terms of quality, but there was some noisy sampling at the end, which made things so slow that this whole speed improvement from non-autoregressive thing was disappearing, basically.
What was the work that you had yesterday?
I don't remember the name, but it's, I think, a pretty famous one, probably from Salesforce.
So we definitely tried. I mean, the whole idea actually of transformers is that you kind of want to take the sentence, you transform it, and then you generate it out. So we tried non-autoregressive, but indeed the sampling from the sampling out of it requires some kind of mechanics that we didn't figure out. So we were trying, inside each layer to have some loss that would try, allow for self-consistency. And but we didn't get any promising results from that yet. But it's definitely an interesting area of research. So if you guys want to try out, that would be very interesting.
Okay, thank you.
Okay, thanks. Any more questions from the audience? then I will ask a question myself. So as far as I understand, those models perform really well on machine translation task, which is really impressive. But I was wondering, since this self-attention mechanism, it just computes the relationship of one word with all the rest of the sentence and all of the text that you are translating, is there any are you aware of any limit on the affordable length of this sentence that you can process with this model? Can it happen that once sentences become too long, you cannot process them efficiently with self-attention, and maybe the results get worse?
I mean, it's definitely true. As I mentioned, so we're generating code, right? So kind of in Near.AI, our input is text of the description of the problem, and the result is program in, let's say, Java or C++. And programs can become very long. So definitely their self-attention, like if you attend to everything, just the square of the n, right? So you have, let's say, 5,000 by 5,000 by the batch, by number of heads. It already takes a lot of memory. So mostly it's memory issue. So that's where restricted self-attention, where you're kind of looking at the windows and just gathering information through hierarchy, helps, because at the end, you don't there's not that many long relationships, so you can get over it with hierarchy, but the local representation, that's what's important. Okay. So yes.
Okay, thank you. So the last call for questions. Okay, if there are no more questions, let's just thank our speaker again. So thank you very much. It was really interesting and very informative. And we hope to see you probably in person in our next hackathons. Thank you and goodbye.
All right, thank you. Yeah, thanks a lot.